There is a question in physics so simple that you answered it before you could walk. Push something, and it pushes back. Heavy things argue harder than light things. That resistance is called inertia. The first law of motion. The first equation every student on Earth is taught. Here is what they left out. Nobody can explain it. Physics has measured that resistance to 1 part in a million billion, flown the roundest objects ever made into orbit to watch it work, and spent billions finding the particle said to give everything mass, which accounts for about 1% of yours. Newton explained the pushback with an invisible stage no experiment can find. Mach explained it with the grip of every galaxy in the sky. Einstein came closest and admitted late in life that the answer had slipped away. By the end of tonight, you will know exactly why the simplest concept in physics has defeated every mind that ever pushed on it. Before we begin, if questions like this are how you like to drift towards sleep, a quick like or subscribe really helps me keep making these. It costs you a moment, and it means more than you know. Now, let's ease in. There is a law of nature you tested before you could speak. You were sitting in a high chair, and you pushed a cup, and the cup slid away from your hand and kept sliding for a moment after you stopped pushing. You did it again. The cup did it again. Somewhere in those repetitions, long before language arrived, you learned the deal that matter offers every living thing. Nothing moves unless something pushes it, and once it moves, something has to stop it. You learned that heavy things argue harder than light things. You learned that the world pushes back. Every human being who has ever lived learned this law the same way, in the body, before school, before words. It is the oldest piece of physics any of us owns. When school finally put words on it, the words came from a book published in 1687. Isaac Newton's Principia Mathematica opens with a statement so familiar that it is easy to forget anyone had to write it down. Every body perseveres in its state of rest, or of uniform motion in a straight line, unless it is compelled to change that state by forces impressed upon it. That is the first law of motion, the law of inertia. An object at rest stays at rest. An object in motion stays in motion. Left alone, matter simply continues. And when you refuse to leave it alone, when you push, the second law tells you exactly what your push will buy. Force equals mass times acceleration. The push you supply, divided by the mass of the thing you are pushing, gives the acceleration you get. Double the mass, and you get half the response. That little letter m, the mass, is the measure of the argument. The number that says how strongly this particular piece of matter will resist your attempt to change its motion. Physicists call that resistance inertia, and it may be the most well-behaved quantity in all of science. It never takes a day off. It is the same on Earth and on the Moon and in the emptiest stretch of intergalactic space. A bag of flour that resists your push with a certain stubbornness in your kitchen will resist with exactly the same stubbornness, while weightless, floating in the middle of nowhere, a billion light-years from the nearest star. Weight changes with location. Weight is gravity's opinion of you, and gravity's opinion depends on where you are standing. Inertia has no opinion and no location. It is just there, in the matter, everywhere, always, to as many decimal places as anyone has ever checked. And we have checked to a lot of decimal places. Modern physics has measured the behavior of inertia more precisely than almost anything else it has ever measured. The predictions built on it guide spacecraft across billions of kilometers and arrive within seconds of schedule. The conservation law that grows out of it, the conservation of momentum, has never failed, not once, in any laboratory, in any particle collision, in any observation of any system anywhere in the universe. If reliability were understanding, inertia would be the best understood thing in existence. You rely on this unexplained law with your life, daily, without noticing. Every seatbelt is a negotiation with inertia. Every airbag is an apology to it. When a car stops suddenly, nothing throws you forward. That is the point almost everyone gets backwards. The car stops, and your body, obeying Newton's first law to the letter, simply continues, at the speed it already had, in the straight line it already had, until the belt or the dashboard, or the windshield, compels it to change its state. Inertia is enforced on your body, with total consistency and zero explanation, every single day of your life. The word itself is a small joke at matter's expense. Inertia comes from the Latin iners, idle, lazy, unskilled. It was Johannes Kepler, the astronomer who worked out the orbits of the planets, who first borrowed the word for physics, though he meant something different by it. Kepler believed matter was lazy, in the sense that it wanted to stop, that rest was what matter was always trying to get back to. The modern meaning, matter's complete indifference to uniform motion, its refusal only of change, had to wait for a later generation. It is worth pausing on that little history, because it tells you the concept was never obvious. The laziness of matter had to be discovered, argued over, renamed, and redefined, and the men doing the arguing were the best minds of their centuries. There is also a subtlety buried in the first law that most of us were never taught, and it will matter enormously later tonight. The first law is not just a special case of the second. It is not merely the second law with the force set to zero. The first law does a separate job. It defines who is allowed to use the second law at all. Force equals mass times acceleration is only true for certain observers, the ones physicists call inertial observers, the ones who are themselves coasting, unaccelerated. Stand on a spinning carousel, and Newton's tidy equation fills up with phantom forces that come from nowhere, pushing you outward, curving every thrown ball. The first law is the membership test. If free objects around you drift in straight lines at steady speeds, you are in the club, and the laws will work for you. Which quietly raises a question the Principia never answers, a question we will spend a good part of tonight inside. Straight lines according to whom? Unaccelerated relative to what? Here is the trouble, and it is the reason we are together tonight. Read Newton's laws again, slowly, and notice what they actually say. They say that matter resists changes to its motion. They say precisely how much it resists. That is what m does in the equation, and that is all they say. Nowhere in the Principia, nowhere in the 3.5 centuries of physics that followed, is there an accepted answer to the question a child can ask in one sentence. Why does it push back? What is doing the resisting? When you shove a stalled car and feel it lean against your hands, not the friction, not the slope, just the sheer mass of it refusing to hurry. What exactly is refusing? The equation assigns the refusal a number and moves on. The number is called mass. The refusal itself is never explained. It is an axiom, a starting point, a thing you assume so that everything else can be derived. Physics did not put a floor under it. Physics built on top of it. This should bother you more than it does, and the only reason it does not is familiarity. Inertia is so woven into experience that it feels like a definition rather than a phenomenon. Of course, things resist pushes. That is just what things are. But listen to how strange the plain facts sound when you say them without the lullaby of habit. Every object in the universe, from a dust grain to a galaxy, resists any attempt to change its state of motion. The resistance is instant. It does not need to be switched on. It acts without any detectable mechanism, without any carrier, without any delay, and it acts identically whether the object is beside a star or in the middle of the greatest emptiness the cosmos contains. Something enforces this. Nobody has ever caught the enforcer. Tonight, we are going to push on the simplest concept in physics and pay attention to what pushes back. We will watch the greatest minds of 4 centuries take their turn at this question. Newton, who answered it with an invisible stage. A fierce Austrian philosopher who answered it with the whole night sky, Einstein, who came nearer than anyone and confessed near the end of his life that the answer had slipped through his fingers. We will meet the most perfect spheres human beings have ever manufactured, launched into orbit to watch space-time itself get stirred. We will visit a July morning in Geneva, when the world believed the origin of mass had finally been found, and we will do the honest arithmetic of what was actually found that day, because it is a smaller fraction of you than almost anyone knows. And at the end, I promise, we will answer the question the title of this video asks, not with a trick and not with a shrug. There is a real answer to why no one can explain inertia, and it is more interesting than any of the explanations that failed, but we are not ready for it yet, and it would mean nothing now. First, we have to feel the full weight of the problem, and the weight, as you are about to see, has been hiding in plain sight since before Newton was born. Because here is the first secret of this whole story, the law of inertia, the most obvious statement in physics, the thing every toddler knows in their bones. For almost 2,000 years, the smartest people alive were certain it was false. The idea that motion continues on its own is not obvious. It is, in fact, flatly contradicted by everything you can see. Kick a ball across a field, and it rolls to a stop. Shove a chair across a floor, and it grinds to a halt the instant you let go. Ride a horse-drawn cart, and the moment the ox stops pulling, the cart stops rolling. Nothing in ordinary experience continues. Everything in ordinary experience quits. And so the first great physicist of the Western world looked carefully at the world he could see and wrote down a law that matched it perfectly, and was wrong. Aristotle taught, in the 4th century before the Common Era, that rest is the natural state of earthly things. A stone's nature is to be down, near the center of the cosmos. Lift it and release it, and it seeks its natural place. That kind of motion, falling, needed no pusher, because it was the object going home. But any other motion, what Aristotle called violent motion, required a mover, continuously, for as long as the motion lasted. The cart moves because the ox pulls. The moment the pulling stops, the moving stops. Motion was not a state you could be in. Motion was an activity, like singing, that ceased the instant the effort ceased. You can feel how reasonable this is. It matches the field, the chair, the cart. It matches your muscles, which know that keeping anything moving in this world costs continuous effort. Aristotle's physics was common sense, written down with genius-level care, and that is exactly why it lasted almost 2,000 years. It survived the fall of empires. It was taught in the universities of Paris and Oxford and Bologna as settled truth, while dynasties rose and fell around it. And all that time, it carried a crack, and the crack was the arrow. Shoot an arrow, and watch what happens. The bowstring pushes the arrow for a fraction of a second, and then all contact ends. And the arrow keeps going, for hundreds of meters, with nothing visibly pushing it. Aristotle's rule says continued motion requires a continued mover. Where is the arrow's mover? Aristotle himself proposed that the air does it. The air displaced from the arrow's tip rushes around behind and shoves it forward, a swimmer's answer, with the medium closing in behind. Even in the ancient world, this satisfied almost no one. Air resists arrows. You can feel it resist your hand out a window. The idea that the same air was also the engine seemed to make the medium do two opposite jobs at once. In the 1300s, a French priest and scholar named Jean Buridan proposed something better. The bowstring, he said, deposits something into the arrow, a quantity he called impetus, and the arrow carries this impetus inside itself, spending it as it flies, the way a hot iron carries heat away from the fire. Heavier bodies could hold more impetus, faster launches deposited more of it. Buridan even suggested, in a spectacular aside, that God might have given the celestial spheres their impetus at creation, and that having no resistance to spend it against, they simply kept turning forever. Stop and honor that idea for a moment, because it is the ancestor of everything we now believe. Impetus is motion as a possession rather than an activity, something an object has rather than something an object does. It is recognizably the grandparent of what physics now calls momentum, but it still had rest as the destination. Impetus ran out. Motion was still, at bottom, a temporary loan against the natural state of stillness. The universe of Buridan still wanted to stop. The man who turned it inside out was Galileo Galilei, working in Padua and Florence in the early 1600s. Galileo did the thing that sounds trivial and changed the species. He stopped asking what motion is for and started measuring what motion does. He rolled bronze balls down polished inclined ramps and timed them with water clocks, with his own pulse, with a precision nobody had bothered to seek, and he noticed a pattern in the geometry. A ball rolling down one ramp and up a second ramp always climbed back to very nearly the height it started from, no matter how shallow the second ramp was. Make the second ramp shallower, and the ball rolls farther, still seeking its original height. Make it shallower still, and it rolls farther still. Now, said Galileo, make the second ramp perfectly flat, remove the climb entirely, and ask what the ball will do. It cannot regain its height, because the ramp never rises. If the surface is perfectly smooth and level and endless, there is nothing to slow the ball and nothing to stop it. It will roll forever. Notice what Galileo did there, because it is one of the most consequential moves in the history of thought. He extrapolated to a case that cannot exist. There are no frictionless ramps and no endless planes. Every real ball in every real experiment stops. Aristotle looked at the world as it presents itself and described what he saw. Galileo looked through the world, subtracted the friction and the air as imperfections, as noise on top of the true law, and described what would happen in a world stripped clean. The stopping, he realized, was never the nature of motion. The stopping was interference. Take away the interference, and the motion simply continues, needing no ox, no air, no impetus, no engine, no reason. Motion is not an activity after all. Motion is a state, as self-sustaining as rest, requiring exactly as much explanation as rest requires, which is none. Galileo saw the consequence, and made it unforgettable with a ship. Lock yourself, he wrote, in the windowless cabin below decks of a large ship, and bring the makings of a small, strange laboratory, flies and butterflies, a bowl of water with fish swimming in it, a bottle dripping into a basin, friends to throw balls with. Study it all carefully while the ship stands still in the harbour. The drops fall straight down. The fish swim in all directions with equal ease. Thrown balls need no extra effort in any particular direction. Now let the ship sail, on calm water, at any steady speed, in a straight line, and study everything again. You will find, said Galileo, not the slightest change. The drops still fall straight. The flies do not pile up against the stern wall. No experiment performed inside the cabin, of any kind, can tell you whether the ship is moving or moored. Uniform motion is undetectable from within, because uniform motion does not do anything to the things that share it. And you have lived this. Every smooth flight you have ever taken, with the coffee poured at 900 kilometers per hour landing neatly in the cup, is Galileo's cabin with wings. There is an irony here worth savoring. The man who explained why the moving earth leaves no trace in our kitchens did it so well that he armed every future physicist against the very question this video is about. Uniform motion needs no explanation. Galileo proved it. Rest needs no explanation. It is just uniform motion at zero. The only thing left that demands a cause, the only event in mechanics where something actually happens, is the change. Acceleration, the swerve, the speeding up, the slowing down. And the response of matter to that change, The pushback, the stubbornness measured by the letter M, was precisely the thing the new physics chose to take as given. The pieces were assembled quickly after that. René Descartes, in his Principles of Philosophy of 1644, stated the law in its clean modern form. Undisturbed motion continues in a straight line, correcting Galileo, who had suspected that unforced motion on Earth would follow the planet's curve. Newton, born the year Galileo died, took the principle as the opening axiom of the Principia and built the whole cathedral of classical mechanics on top of it. The system worked so well that its own success buried the question at its base. The equations predicted the tides, the orbits of moons, the return of comets to the year. Nobody interrogates a foundation, while the building on top of it is conquering the world. But one man did, the author of the cathedral himself. Newton, alone among his contemporaries, understood exactly what he had assumed and refused to leave it unexamined. He could define force, and he could define mass well enough to calculate with it, though his definition, mass as density times volume, quietly runs in a circle, since density is just mass divided by volume, a circle that would be noticed loudly 2 centuries later. What he could not define, and knew he could not define, was the thing the whole structure stood on, the difference between real motion and apparent motion, between truly accelerating and merely seeming to. His laws only work for some observers. Something in the universe decides which ones. And to catch that something in the act, Newton proposed one of the simplest experiments in the history of physics, a bucket, a rope, and a puzzle that is still not settled. So do not let anyone tell you the question of inertia is naive. It took our species 20 centuries to state the law correctly. It has taken us 3.5 more so far to fail to explain it. The most important experiment in the history of this question requires no laboratory, no funding, and no mathematics. Newton described it in the Principia, and you could perform it tonight with what is in your garage. Take a bucket, half filled with water, hang it from the ceiling by a rope. Twist the rope, around and around, until it is wound tight. Then let go, and pay attention, because in the next 30 seconds you are going to watch the deepest crack in classical physics open in slow motion. Come stand in the cellar and watch it properly. It is dark and quiet, and the wound rope creaks once as you release the bucket. The bucket begins to spin, faster as the rope unwinds, and the water inside does nothing. The bucket walls are turning. The water sits still, its surface flat and calm as a mirror, ignoring the container whirling around it. At this first moment, notice the facts carefully. The relative motion between bucket and water is at its greatest. The bucket races, the water rests, and the water's surface is perfectly flat. Now wait. Friction between the walls and the water slowly recruits the water into the rotation, layer by layer, the outside first. The water begins to turn, then to turn with the bucket until the two rotate together as one. And as the water joins the spin, its surface changes. It sags in the center and climbs at the edges, curving upward into a shining concave bowl. Now notice the facts again. Bucket and water are moving together. The relative motion between them is zero, exactly as it was before you released the rope. And yet the surface is curved. Grab the bucket suddenly and hold it still. The water keeps spinning inside the stopped container, and the surface stays curved. Relative motion, at a maximum again, curve still there. Something real is happening to that water. The climb up the walls is not an appearance or a convention. It is centimeters of cold liquid physically standing above its own rest level, and you could float a cork on it and watch the cork slide outward. The water is telling you, in the plainest possible language, that it knows it is rotating. But here is Newton's terrible, simple question. Rotating relative to what? Not relative to the bucket. We have just seen that the bucket is irrelevant, since the curve appears when their relative motion is zero and vanishes when it is greatest. Not relative to the cellar in any obvious mechanical way. The walls exert no pull on the water, and you could brick up the cellar or tear it down without changing the experiment. Then relative to what does the water rotate? What is the thing whose opinion the water's surface reports? You already know, in your body, the strange asymmetry the bucket is exposing. Uniform motion is silent, sealed in Galileo's cabin, or cruising in a night train with the blinds down. No sense you possess can detect the speed, but rotation announces itself. Close your eyes on a playground merry-go-round, and you know instantly that you are turning. Your inner ear reports it. Your arms drift outward. Your stomach files a complaint. A figure skater feels her own spin with her eyes shut. A pilot in cloud can be deceived about many things, but a spinning aircraft writes itself into the fluid of the inner ear. Acceleration, unlike velocity, is absolute. You do not need to peek outside to measure it. And that is precisely the mystery. Measured against what? The skater's closed eyes see no stars. The water in the bucket has no inner ear. Yet both of them answer to some standard of rotation that is present everywhere, in every cellar, and every cockpit, and every cubic centimeter of the cosmos, hidden and unanimous. Physicists would later formalize the skater's certainty into an instrument, the accelerometer, a small mass on a spring inside a box. It reads zero when you coast, and swings when you turn, with no window and no reference mark anywhere inside it. There is one riding in your phone right now, keeping the screen upright, a sealed, blind device that somehow always knows. Newton's answer was as bold as it was strange. Absolute space. Space itself, he said, is a real thing. Not the objects in it, but the arena itself, an immense, motionless, invisible stage that exists whether or not anything occupies it. True motion is motion with respect to this stage. The water curves when it rotates relative to space itself, and the flat surface marks true rest with respect to the same. The universe, in Newton's picture, comes equipped from the factory with a built-in standard of rest and rotation, and inertia is matter's grip on that standard. Push a body, and absolute space is the referee that says it accelerated. Newton then sharpened the argument with a second thought experiment, more austere than the bucket, and aimed at exactly the objection a skeptic would raise. Imagine, he said, two globes, joined by a cord, alone in an immense emptiness. No stars, no cellar, no earth, nothing else in existence. Set them revolving about their common center, like a slow bolas. Nothing visible moves relative to anything. There is nothing else to move relative to. And yet, said Newton, the cord will carry tension. You could measure it with a spring scale spliced into the line. Increase the spin, and the tension rises. Stop the spin, and the cord goes slack. The tension is real, measurable physics, occurring in a universe with no landmarks whatsoever. And so, Newton concluded, the rotation it reveals must be rotation relative to something that is not a landmark, not a body, not visible, space itself. Sit with how disturbing this answer is, because familiarity has sanded off its edges. Absolute space, as Newton himself effectively conceded, is a thing that acts on everything and is acted upon by nothing. It grips every bucket of water and every spinning globe in the cosmos, enforces the distinction between true and apparent motion everywhere and always, and yet it cannot be seen, touched, weighed, sampled, or detected by any means whatsoever, except through the very effects it was invented to explain. It has no parts you can mark, no position you can lose, no motion of its own you could ever measure. Uniform motion through it leaves no trace at all. Galileo's ship guaranteed that. So you can never know your speed with respect to the very thing that defines speed. It is a referee that never shows itself, employed by every object in the universe, paid in nothing, seen by no one. Newton knew all of this. That is what separates him from the textbook version of Newton. In private manuscripts, and in the careful, hedged language of the Principia's opening discussion, he wrestled with the metaphysics. Some scholars believe he ultimately grounded absolute space in the omnipresence of God, the divine sensorium, the stage held steady by the one being who needed no stage. Whatever his private resolution, his public position was ruthlessly practical. The effects are real, the mathematics works, and the water does not care about your philosophical discomfort. The curve in the bucket is data. Explain it or accept my stage. For 200 years, physics accepted the stage. It had every practical reason to. Mechanics built on absolute space predicted the world with a precision no rival system could touch. The tides, the wobble of the Earth's axis, the return of Halley's comet on schedule, eventually the discovery of Neptune by pure calculation, a planet found at the tip of a pen because Uranus was being tugged from its inertial path by something unseen. Every one of those triumphs used inertia as its master key, and inertia meant resistance to acceleration with respect to absolute space. The stage was invisible, undetectable, philosophically monstrous, and it delivered, decade after decade, the most accurate predictions in the history of human knowledge. And yet the unease never fully died, it just went quiet. It survived in a line of skeptics who kept asking the impolite question, Bishop Berkeley within Newton's own lifetime, insisting that motion in a universe of one body is meaningless. Leibniz, in his famous correspondence, arguing that space is nothing but the order of relations among things, and that an empty stage with nothing on it is a fiction. Words can build, but reality cannot hold. Their objections were profound, and they lost anyway, for the oldest reason in science. They had no equations, and Newton did. Metaphysical elegance does not compute cometary orbits. For 2 centuries, the skeptics of absolute space were a footnote, muttering, at the back of a victory parade. But notice what the muttering was about, because it is the thread we will pull for the rest of the night. If the skeptics were right, if space is only relations between things, if motion only means motion with respect to other matter, then the water's curve must be caused by matter. Some actual, physical stuff must be the thing the water rotates relative to. Some actual stuff must be the source of the resistance you feel when you push. Look around the cellar. The bucket is disqualified. The cellar walls do nothing. The earth beneath, perhaps. But the experiment behaves identically at any latitude, and calculations show the nearby planet's influence of this kind is next to nothing. Keep looking. Go up the stairs, out the door, into the night, and keep raising your eyes past everything nearby, past the moon, past the sun, past every star whose name anyone knows. What is left, when everything close has been ruled out, is everything far. The only candidate remaining is all of it, the total combined matter of the universe, the great slow wheel of the galaxy, and the billions of galaxies beyond it, the whole freight of creation, standing in the night sky like a jury. It took 200 years for someone to have the nerve to point at the sky and say it out loud. That is what the water is rotating relative to. Them, the stars, all of them, together. And the man who finally said it did not offer it as poetry. He offered it as a debt physics owed, and a fierce, half-blind Austrian would collect. Before anyone could hope to explain inertia, physics had to notice that inertia was keeping a secret, and the secret hides inside a single letter. Look again at the second law. Force equals mass times acceleration. Now look at Newton's other great equation, the law of universal gravitation. The attraction between two bodies is proportional to the product of their masses, divided by the square of the distance between them. The same letter m appears in both equations, and if you have ever taken a physics class, it never occurred to you to question it. But those two m's have completely different jobs, and there is no reason in Newton's physics, none, why they should be the same number. The mass in the second law is inertial mass. It measures resistance, and it has nothing to do with gravity. Push a bowling ball sideways, on frictionless ice, in deep space, anywhere, and inertial mass is what fights your push, equally in every direction, in the total absence of any gravitational field you care about. The mass in the law of gravitation is gravitational mass, and it measures something else entirely: how strongly a body couples to gravity, how hard the earth pulls it, and how hard it pulls the earth. One is a body's stubbornness. The other is a body's gravitational charge. Physics has a precise parallel that shows how strange their equality is. Electricity also has a coupling number. Electric charge measures how strongly a body responds to electric fields, just as gravitational mass measures how strongly it responds to gravity. And electric charge has nothing whatsoever to do with inertia. An electron and a proton carry exactly the same size of electric charge, yet the proton has nearly 2,000 times the inertial mass. Nobody expects charge to equal inertia. The two numbers describe unrelated things, and nature treats them as unrelated. But gravity's coupling number, alone among all the forces, tracks inertial mass perfectly. Double a body's stubbornness, and you have exactly doubled its weight. Halve its weight, and you have exactly halved its stubbornness. Always. For every material. Everywhere. This equality has a consequence you have seen with your own eyes. Everything falls at the same rate. The Earth pulls a heavy object harder, but the heavy object resists acceleration more, in exactly the same proportion, and the two effects cancel to the last decimal place. The pull is doubled, the stubbornness is doubled, the acceleration comes out identical. Drop a cannonball and a pebble, and they keep pace all the way down, not because gravity treats them equally. It does not. It pulls the cannonball far harder, but because the cannonball is precisely as much harder to move as it is harder pulled. The legend says Galileo demonstrated this from the Leaning Tower of Pisa. The historians say the legend was probably invented by his devoted secretary decades later. But the experiment was eventually performed properly, on the finest stage imaginable. In 1971, standing in the dust of the lunar highlands, Apollo 15 commander David Scott held out a geologist's hammer in one glove and a falcon's feather in the other, and let them go together in the airless silence. On the television feed, watched by millions, the hammer and the feather fell side by side, unhurried, perfectly together, and struck the moon at the same instant. "Well," said Scott, "that proves Mr. Galileo was correct. The question is how perfect the agreement really is, and the campaign to find out spans 3 centuries and 12 orders of magnitude, one of the great quiet epics of measurement. Newton himself opened it. He built pendulums with identical wooden boxes for bobs, and filled them by turns with gold, silver, lead, glass, sand, salt, wood, water, and wheat, deliberately choosing the most different materials his world could offer. If inertial and gravitational mass differed by substance, pendulums of different filling would swing at different rates. To about 1 part in 1,000, Newton found, they did not. 2 centuries later, a Hungarian baron raised the stakes enormously. Laurent Oetvers, working in Budapest around the turn of the 20th century, hung pairs of different materials from a torsion balance, a horizontal bar suspended on a fine fiber, the most sensitive force-measuring instrument of its age. His logic was elegant. Sitting on the rotating Earth, every object is subject to gravity, which couples to gravitational mass, and to the centrifugal effect of the planet's spin, which couples to inertial mass. If the two masses were not identical, different materials would hang at minutely different angles, and the fiber would twist. Oetvers spent decades listening for that twist and heard nothing, down to a few parts in a billion. The equivalence held, 1,000,000 times more precisely than Newton could check. The 20th century turned the screw further. Robert Dicker's group at Princeton, in the 1960s, redesigned the experiment to use the sun's pull instead of the Earth's, letting the planet's daily rotation modulate any signal, and push the limit to about 1 part in 100 billion. The Ethert-Wash group at the University of Washington, the name is a pun honoring the Baron, refined rotating torsion balances through the 1990s and 2000s to roughly 1 part in 10 trillion. Along the way, the technique produced one famous false alarm. In 1986, physicist Ephraim Fishbach reanalyzed Oatefuss's old data, found a suspicious pattern correlated with the composition of the test bodies, and announced evidence for a fifth force of nature, a new interaction, screened at long range, that would break the equivalence. For a few exhilarating years, laboratories worldwide hunted it, on towers and cliffs, and down mine shafts. It evaporated. The pattern was an artifact. The follow-up experiments found nothing, and the episode ended up strengthening the very principle it challenged, because the hunt drove the instruments to new precision. The current record belongs to space. A French satellite mission called Microscope, flying from 2016 to 2018, carried 2 concentric cylinders of deliberately mismatched material, one titanium, one an alloy of platinum and rhodium, chosen to differ in almost every property matter has, and let them free fall around the Earth for months inside a drag-compensated shell, an environment quieter than any laboratory on the planet's surface. If the 2 cylinders fell even infinitesimally differently, tiny electrostatic forces would be needed to hold them centered, and those forces would be the signal. The final analysis, published in 2022, found the 2 materials fall identically to about 1 part in 10 to the 15th power, 1 part in 1,000,000 billion. Numbers that small defeat the imagination unless you translate them. So translate it. If a difference that size were applied to a journey the width of a human hair, Microscope could have detected the discrepancy on a trip several times the distance from the Earth to the Moon. It is worth lingering inside the Microscope result, because the delicacy of it borders on the absurd. At the precision the mission demanded, almost everything in the universe counts as a disturbance. The gentle pressure of sunlight on the satellite's body, a push comparable to the weight of a grain of sand, had to be measured, modeled, and cancelled by whisper-quiet thrusters, or it would have swamped the signal 1,000 times over. The residual wisps of atmosphere at 700 kilometers of altitude mattered. The gravitational tug of the satellite's own components on the test masses mattered, and was mapped to the gram. Engineers were, in effect, weighing the honesty of the universe, while the universe drummed its fingers on the instrument. And through all of it, titanium and platinum fell together, indistinguishable, orbit after orbit after orbit, for month upon month, 2 materials that agree about nothing else, agreeing about this to 1 part in 1,000,000 billion. There is also a stranger way to say what all these experiments found, and it is worth planting now. If everything falls identically, every substance, every mass, every structure, then falling is not really a response that varies from object to object, the way responses to electric fields vary with charge. Falling is universal. It is less like a force acting on things, and more like something the location itself does to whatever occupies it. Every object released above the Earth, from a feather to an anvil to a beam of light, immediately agrees on one single trajectory, as if the path were already there, drawn into the space, waiting, and the objects were merely obeying the room rather than answering a pull. Keep that image. It is about to become the 20th century. Physics has no more precisely confirmed null result. And a perfect coincidence, in science, is never treated as a coincidence. It is treated as a signpost. When 2 quantities with utterly different definitions agree to 15 decimal places across every material, every temperature, every place, and every era anyone has tested, the working assumption of every physicist is that they are not two quantities at all. They are one thing, seen twice. One phenomenon wearing two costumes, and the costumes fooled us because we invented the wardrobe. Somewhere beneath the second law, and the law of gravitation, stubbornness and weight must be the same fact about the world. Whatever inertia turns out to be, it is now required to also be whatever gravity grabs. Any explanation of the pushback in your hands must simultaneously explain the pull in your feet, or it is wrong. Hold on to that requirement, because everything ahead turns on it. In the early 20th century, one man took this exact coincidence, the equality nobody could explain and everybody had stopped seeing, and decided it was not a detail of mechanics, but the master clue, the loose thread at the edge of the whole Newtonian architecture of forces and stages. Pulling it would cost him 8 years and give him, in his own words, the happiest thought of his life. But before his happiest thought could happen, someone had to break absolute space for him. Someone had to stand up, point at Newton's invisible stage, and call it what it was. That demolition came from Vienna, from a physicist-philosopher with a beard like a prophet and no patience whatsoever for things that could not be observed. And his name is stitched into this story so deeply that Einstein himself named the principle after him. Ernst Mach did not look like a demolition expert. Photographs show a compact Austrian professor with a great grey beard and kindly, skeptical eyes. A man who spent his days studying shock waves and the psychology of sensation, whose name would end up attached, almost by accident, to the speed of sound. Mach 1, Mach 2, that is him. But his deepest work was a kind of intellectual hygiene. Mach believed, with a ferocity that organized his entire life, that science must speak only of what can be observed. Concepts that could never, even in principle, show themselves to an instrument or a sense organ were not profound truths in his eyes. They were habits of language that had hardened into furniture, and he made it his business to haul them out of the house. In 1883, he published The Science of Mechanics, a history and critique of physics from its foundations up. And when he arrived at Newton's absolute space, he did not tiptoe. He treated it the way he treated every unobservable, as a squatter in the house of physics, living rent-free for 200 years. His attack on the bucket argument is 2 sentences of pure acid, and the whole rest of this video grows out of them. Newton's experiment, said Mach, shows only that rotation relative to the bucket's walls produces no centrifugal effect in the water, and that rotation relative to the earth and the distant heavenly bodies does. That is all it shows. Nobody knows, he went on, how the experiment would turn out if the bucket's walls were made ever thicker and more massive, until they were leagues thick, because the experiment has never been done and cannot be done. Read those sentences again slowly, because they perform a maneuver of devastating simplicity. Newton observed water curving and concluded it must be rotating relative to invisible space, because it visibly was not rotating relative to the bucket. Mach points out that the water was visibly rotating relative to something enormous, something luminous, something hanging in plain sight every clear night of every year of every human life, the earth, the sun, the stars, all of it. Newton looked past the entire visible universe to blame an invisible stage. Mach simply refused to look past it. When the water climbs the walls, it is accelerating with respect to the total matter of the cosmos. Why invent anything else? The universe is right there. Follow Mach's logic where it leads, because it leads somewhere astonishing. If the curve in the water is caused by rotation relative to the distant matter of the universe, then the distant matter of the universe is doing something to the water, physically, actually doing something. And then the same must be true of every inertial effect. The lurch you feel when a bus brakes. In Newton's world, that is your body's relationship with absolute space. In Mach's world, there is no absolute space. so it can only be your body's relationship with everything else. With the floor, and the street, and the planet, yes, but overwhelmingly, when the accounting is done, with the distant galaxies, because there is so unimaginably much more of the universe out there than there is here. Inertia, in Mach's picture, is not a private property that each object carries in its own pocket. Inertia is a relationship. Matter resists acceleration because all the other matter in existence somehow holds it, the way a ship's position is held by the anchor, except this anchor is everything, everywhere, all at once. Mach pushed the point with a symmetry argument that still produces vertigo when you take it seriously. Consider the bucket again, he said in effect, and now consider the reverse experiment. Hold the bucket perfectly still and set the entire universe rotating around it. Every star, every galaxy, the whole sky wheeling about the motionless water. Newtonian physics says these are utterly different situations. In the first, the water truly rotates and curves. In the second, the water is truly at rest and stays flat while the scenery spins. But how, Mach demanded, could you ever tell the difference? All any observer can ever measure is the relative rotation between water and sky, and it is identical in both cases. If physics is about what can be observed, the two situations are not two situations. They are one situation described twice, and so the water must curve in both. Spin the sky, and the water should climb the walls. The stars, in other words, do not merely mark the frame against which rotation is measured. On Mach's reading they create it. The universe, turning, would drag the standard of rest around with it. There is an instrument that makes Mach's cosmic bookkeeping feel physical, and you have probably stood in front of one without hearing what it was whispering. In science museums all over the world hangs a Foucault pendulum, a heavy bob on a long wire, swinging with hypnotic patience above a circle of toppled pins. Set swinging in Paris, as Léon Foucault first did in 1851, the pendulum's swing plane slowly rotates, completing its circuit in about 32 hours at that latitude. The standard explanation says the pendulum swings true while the Earth turns beneath it, but swings true with respect to what? Not the building. The building is bolted to the turning planet, not the Earth, not even quite the Sun. Track the swing plane with enough care, and you find it holds itself steady against the frame of the distant universe. The pendulum in the museum lobby, keeping faith with matter, so remote that its light set out before the Earth existed. Nothing about the nearby world instructs it. The wire hangs from a local ceiling, the bob was forged in a local foundry, and the swing ignores all of it, saluting the far side of everything instead. Stand there watching it some afternoon, and let the fact land. The most distant objects in creation appear to have more authority over this brass weight than the building it hangs in. Mach looked at that authority and said, "There is your inertia. That grip is the thing you have been calling mass. Take the pendulum to the North Pole, and the whisper becomes a shout. At the pole, the geometry is perfectly clean. The swing plane rotates through a full circle in exactly one sidereal day, 23 hours and 56 minutes, which is the time the Earth takes to turn once with respect to the stars, not with respect to the sun. The pendulum does not track our noon. It tracks the far universe's clock, precisely, as if wired to it." Foucault's demonstration, incidentally, caused a sensation precisely because it needed no astronomy. For the first time, anyone standing in a hall in Paris could watch the Earth rotate, could see, over a single quiet hour, the planet turning under a brass bob. Crowds queued at the Panthéon through the spring of 1851 to watch pins fall. What none of them were told, because nobody yet framed it this way, was the darker half of the demonstration. They were also watching an unexplained loyalty, a local object taking its orders from the far side of the sky. And the grip is on you too. That is the part that should keep you awake tonight, or perhaps carry you gently into sleep. Every push you have ever felt push back. Every suitcase that lagged your arm, every lurch of every train, the seat pressing into you as a plane gathers speed down a runway. Every one of those sensations, if Mac is right, was the felt presence of the whole universe, arriving through your own body, instantly, from everything that exists. The resistance in your muscles when you rise from bed tonight would be, quite literally, the most non-local thing you will ever touch. An agreement between your bones and galaxies whose light has not reached you and never will. You have been in conversation with the entire cosmos since before you could speak, and you thought it was just the heaviness of things. There is even a rough arithmetic that explains why the far universe would outvote the near one, strange as that sounds. Whatever influence distant matter exerts on local inertia, the natural guess, modelled on gravity, is that it weakens with distance, falling off in proportion to 1 over the separation. But the amount of matter available grows with distance much faster than the influence shrinks. Each successive shell of sky, twice as far away, contains far more galaxies than the shell before it. Run the numbers with that gravitational style weighting, and the ledger tips overwhelmingly outward. The earth beneath your feet contributes almost nothing to your inertia, the sun a whisper, the Milky Way a murmur, and the faint, uncountable galaxies near the edge of the observable universe would carry nearly the whole vote. If Mac is right, the resistance of your coffee cup is administered, almost entirely, from beyond the reach of any telescope's naming. The nearest things govern your weight. The farthest things, on this view, govern your mass. Mac never built the theory. That has to be said plainly, because his name is now attached to a principle he stated only in fragments and refused to formalize. He offered no equation for how distant matter generates local inertia, no mechanism, no force law, no prediction, only the relentless observation that Newton's alternative was a phantom, and that the universe of actual matter was sufficient and present, and had never been given its audition. He was in some ways a difficult prophet. Late in life he even resisted the existence of atoms, demanding to be shown one before he would believe, but his critique detonated exactly where it needed to. Among the young physicists who read The Science of Mechanics and felt the Newtonian floor tilt was a Swiss patent clerk, who would later write that Mach's book had shaken him out of a dogmatic slumber. The clerk agreed that absolute space had to go. He agreed the equality of the two masses was no accident. And in 1907, sitting at his desk in Bern between patent applications, he had the thought he would call the happiest of his life, a thought about a man falling off a roof. In 1907, Albert Einstein was 28 years old and working 6 days a week at the Swiss Federal Patent Office in Bern, examining applications for electrical devices. He had already, 2 years earlier, produced the special theory of relativity, the physics of uniform motion, Galileo's ship rebuilt, for a universe where light's speed never changes, along with the papers on the quantum of light and the reality of atoms, any one of which would have secured a career. But special relativity had 2 loud gaps. It said nothing about gravity, and it said nothing about acceleration. It inherited Newton's inertial frames without explaining them, a cathedral built on the same unexamined floor. Einstein was writing a review article about his own theory when the thought arrived. He was sitting in a chair in the patent office, he later recalled, when it struck him. If a person falls freely from the roof of a house, he does not feel his own weight. He would later call it der glücklichste Gedanke meines Lebens, the happiest thought of my life. Stay with the falling man for a moment, because everything turns on what he does not feel. As he falls, and set aside the air, as Galileo taught us to, he feels nothing pulling him. Weight, the sensation, has vanished. If he releases his keys and his hat, they do not drop away from him. They float beside him, keeping perfect company, because everything falls identically. That is the ancient equality of the two masses, the fact confirmed from Newton's pendulums to the hammer and the feather in the lunar dust. Inside his falling world, there is no experiment he can perform, with keys or hats or anything else, that will reveal gravity at all. Seal him in a windowless falling box, and his situation is indistinguishable from floating in deepest space, infinitely far from any planet. Gravity, from the inside, is not merely weak or hidden, it is gone. Now run the logic the other way. Put the same man in the same windowless box, far out in empty space, and accelerate the box, hook it to a rocket, and pull it forward at 9.8 meters per second, faster every second. The floor rises against his boots. His keys, released, appear to fall to the floor. His hat feels heavy on his head. Everything inside behaves exactly, precisely, as it would in a stationary room on the surface of the earth, and no experiment inside the box can tell the difference. Acceleration manufactures perfect counterfeit gravity, and free fall perfectly erases real gravity. The two, Einstein proposed, are not merely similar. Locally, they are the same thing. He named this the equivalence principle, and it is the two-mass coincidence from earlier tonight, promoted from a curiosity into the axis of a new physics. Inertial mass equals gravitational mass, because being pushed and being pulled were never two phenomena in the first place. It took Einstein 8 more years to build the theory that could carry that thought, and the struggle nearly broke him. Years of dead ends, a wrestle with mathematics he had to learn as he went, a final sprint in November 1915, racing against his own errors. What emerged, the general theory of relativity, did something to inertia that no one had imagined. It made inertia and gravity the same phenomenon by redrawing what a straight line is. In Einstein's universe, mass and energy curve the geometry of space-time itself, not space alone, but the four-dimensional weave of space and time together. And matter, left utterly alone, does the laziest possible thing in that curved geometry. It follows the straightest available path, called a geodesic, a thrown stone, the arcing moon, the falling man. None of them are being pulled by anything. They are coasting. Each one is doing the exact four-dimensional equivalent of Galileo's ball rolling forever on the endless plane, continuing, undisturbed, in the straightest line the local geometry permits. The curve you see in the stone's flight is not a force bending its path. It is the path, drawn in a geometry your eye was not built to see. Newton's first law does not merely survive in general relativity, it is enlarged into the whole law of motion. Everything free falls, and free fall is inertia. Feel what this does to the question we have been carrying since the cellar. In Newton's physics there were two mysteries: why matter resists acceleration, and why gravity pulls all matter identically. Einstein fused them into one. Weight, the sensation you are feeling right now, in your chair or your bed, is reclassified. You are not being pulled down. Per general relativity, you are being pushed off your geodesic, continuously, by the floor. Your natural motion, the path space-time has drawn for you, plunges toward the center of the earth, and the ground refuses to let you take it, shoving upward against your body, year after year. What you have called your weight, all your life, is the feel of that refusal. An accelerometer proves it with a certainty that still startles physicists' students. Resting on a table, it does not read the pull of gravity, it reads the table's push. Drop it, and while it falls freely, doing what gravity supposedly makes things do, it reads exactly 0. Falling is the one state in which nothing whatsoever is happening to you. Inertia and gravity, resistance and weight. One phenomenon, one geometry, one law. The equivalence of the box and the planet also handed Einstein a prediction machine, and he cranked it immediately. If accelerating upward is indistinguishable from standing in gravity, then whatever happens in the rocket must happen on the Earth. Fire a beam of light across the accelerating box, and in the time the light crosses, the floor surges upward, so the beam, perfectly straight in its own right, strikes the far wall slightly below where it entered. Inside the box, that looks like the light bending downward. Therefore, said Einstein, gravity must bend light. A claim tested against the stars at the eclipse of 1919 and confirmed the result that made him, overnight, the most famous scientist alive. And a clock at the ceiling of the box must run fast compared to a clock on the floor. Therefore, time itself must run at different rates at different heights in gravity. A prediction so delicately true that the clocks in your phone's navigation system must correct for it every day to keep your blue dot on the road. Let the new picture in slowly, because it deserves an unhurried minute, and this is a good place in the night to breathe. Think of the International Space Station and the astronauts drifting inside it, pens and droplets of water hanging in the air around them. The old language says they float because they have escaped gravity. They have not. At 400 kilometers up, the Earth's gravity is still almost 9/10 of what you feel now. They float because they are falling. The station falls toward the Earth continuously, endlessly, and moves sideways so fast, about 28,000 kilometers per hour, that the ground curves away beneath it exactly as fast as it drops. Orbit is permanent free fall with good aim, and in Einstein's language, those astronauts are the only people anywhere near the Earth who are actually obeying Newton's first law. They are the ones moving in a true straight line, a geodesic, undisturbed, unforced, at rest in the deepest sense the universe recognizes. It is everyone down here, pressed against floors and mattresses and chairs, who is being accelerated, all the time, without ever going anywhere. The sleepers are being pushed, the fallers are at peace. John Wheeler, the great American physicist, compressed the whole theory into one sentence worth carrying to sleep. Space-time tells matter how to move. Matter tells space-time how to curve. And Mark seemed, for one glorious decade, to be vindicated in full. Einstein had read The Science of Mechanics as a student, and he credited it always. He corresponded with the old man, visited him in Vienna, and consciously built his theory as the answer to Mach's demand. Absolute space was dead. In general relativity, space-time is no fixed stage but a dynamic participant, curved and bent by matter. Local inertial frames, the falling boxes, the coasting geodesics, are not decreed by an invisible referee. They are shaped by the distribution of mass and energy. The stars really do have a say in what counts as unaccelerated here. In 1918, Einstein gave the demand a name, coining it in print, Mach's principle, the idea that the inertia of each body is determined by the matter of the universe as a whole. For a time he held it as a foundation stone of his own theory, insisting that in a truly Machian universe, a particle alone in an otherwise empty cosmos should have no inertia at all, because there would be nothing to define its motion against. The bucket, the stars, the falling man, the great new geometry, it all seemed to be converging on a single, luminous conclusion. Inertia was about to be explained as the grip of everything upon everything, written in the curvature of space-time. It is one of the most poignant almosts in the history of science, because general relativity, Einstein's own creation, the most beautiful theory physics possesses, was about to turn on Mach and on its maker. The theory would indeed prove that matter shapes inertia's frame, measurably, spectacularly, with spinning planets, stirring space-time like spoons in honey, as we will see in the next part, with some of the most exquisite machines ever built. But the same equations would also permit universes Mach forbade, worlds with inertia and no matter, worlds that rotate with respect to nothing. And Einstein, with a lifetime's honesty, would eventually concede that the principle bearing his hero's name could not live inside his theory. The down payment was real. The full debt was never paid. Both halves of that story are ahead of us, and the first half glitters. 4 perfect spheres, a star called IM Pegasi, and a prediction from 1918, measured in thousandths of an arcsecond, half a century after everyone involved was dead. If matter truly has a say in what counts as rotation, if Mach was even partly right, then general relativity makes a promise that can be checked. In 1918, within 3 years of Einstein's field equations, 2 Austrian physicists, Josef Lense and Hans Thirring, sat down with the new mathematics and calculated what a spinning mass does to the spacetime around it. The answer was extraordinary. A rotating body does not merely curve spacetime the way any mass does, it drags it. The local inertial frames, the falling boxes, the standards of non-rotation, the very thing Newton's water was answering to, get pulled around a spinning mass like honey around a turned spoon. Sit near a rotating planet, and the meaning of not rotating itself slowly revolves. Inside a sufficiently massive rotating shell, they showed, a Foucault pendulum would be deflected, tugged into partial agreement with the shell's spin. This is exactly the flavor of effect Mach demanded. Matter, by its motion, reaching out and adjusting the inertial compass of its neighborhood. Thirring did the shell calculation with Mach explicitly in mind. The trouble was the size of the number. For anything humans could build, the dragging was hopelessly beyond measurement. Even for the whole spinning Earth, the effect at orbital altitude amounts to a reorientation measured in tens of thousandths of an arcsecond per year. The prediction sat in the literature for 8 decades, waiting for instruments worthy of it. The instrument that finally answered is, by some accountings, the most precise machine human beings have ever flown. It was called Gravity Probe B, and its story is almost as improbable as its target. Conceived around 1960, championed for 4 decades by Stanford physicist Francis Everett, through funding battles that nearly killed it more than a dozen times, it finally launched in April 2004, a satellite built around a thermos of superfluid helium, carrying 4 gyroscopes and a telescope into a polar orbit 642 kilometers up. Its mission was brutally simple to state. Point the telescope at one star, IM Pegasi, a binary star about 300 light-years away, chosen because radio astronomers could track its own tiny motion against the far universe. Align the spinning gyroscopes with that star, then watch, for a year, to see whether the gyroscopes drift. Step into the clean room where those gyroscopes were made, because they deserve a scene of their own. Under white light and filtered air, a technician holds up a sphere of fused quartz the size of a ping-pong ball, and it may be the roundest object our species has ever manufactured. Its surface departs from a perfect sphere by no more than about 40 atomic layers. If you inflated this ball to the size of the Earth, its tallest mountain would stand roughly 2.5 meters high. It is coated in a whisper of niobium, thinner than a soap bubble's wall, so that when it is chilled near absolute zero, the coating becomes superconducting, and the sphere's spin direction can be read from the quantum magnetism of the spinning metal. Read without touching, because nothing may ever touch it. In orbit, each sphere is suspended electrically inside its housing, spun up to about 4,000 revolutions per minute by a breath of helium gas that is then pumped away to a vacuum and left to coast, a perfect Newtonian object, more alone than any spinning thing in history, twirling in the dark, with nothing to answer to but space-time itself. The choice of guide star was itself a small epic. IM Pegasi had to be bright enough for the onboard telescope, close enough to the orbital plane, and, crucially, trackable by radio interferometry against quasars billions of light-years away, so that the star's own drift across the sky could be subtracted. The gyroscopes were referenced to a star. The star was referenced to quasars. The quasars, so distant that no motion of theirs is detectable, stood in for the frame of the universe itself. The chain of custody for not rotating ran, link by link, from a quartz sphere in orbit to the far edge of everything visible. General relativity made 2 predictions for what those spheres would do. The first, the geodetic effect, the gyroscope tipping because it orbits through curved spacetime, was the larger, 6,606 thousandths of an arcsecond of drift per year. The second was the ghost, frame dragging, the Earth's rotation hauling the local inertial frames around with it, twisting the gyroscope's axes by just 39 thousandths of an arcsecond per year. A thousandth of an arcsecond is the width of a human hair seen from 16 kilometers away. The mission flew. The data came down, and then came 5 grinding years of analysis, because tiny patches of electrostatic charge on the spheres produced wobbles nobody had fully anticipated, and the team had to model them out while the world watched skeptically. Those 5 years were their own quiet drama. Rumors circulated that the mission had failed, review panels wavered, funding gapped, and was rescued, at one point, partly by a Saudi royal donation. The physicists lived inside the wobble models, separating a signature of 39 thousandths of an arcsecond per year from disturbances 100 times larger, knowing that a community of skeptics would test every assumption. When Everett, by then in his late 70s, having given the project essentially his entire career, finally presented the result, he had waited longer for his answer than Peter Higgs would wait for his particle. In 2011, the final numbers were published. Geodetic drift, measured at 6,601.8 thousandths of an arcsecond per year, against the predicted 6,606, agreement within 0.25%. Frame dragging, measured at 37.2, with an uncertainty of about 7, against the predicted 39.2. Both effects real, both as Einstein's theory demanded, calculated by 2 men in Vienna in 1918, confirmed by 4 quartz spheres reading the rotation of spacetime half a century after everyone involved in the prediction had died. Independent confirmations bracketed it. 2 brass and aluminum spheres, called Lagios, passive satellites covered in mirrored corner reflectors, launched in 1976 and 1992 for laser ranging, had their orbits measured so precisely over decades that analysts, led by Ignazio Ciuffalini, teased out the frame-dragging twist of the orbital planes themselves, later sharpened by a dedicated follow-up satellite, Laris. And in 2020, the effect graduated from planets to dead stars. Radio astronomers led by Vivek Venkatraman Krishnan published 20 years of timing of a pulsar called J1141-6545, a radio beacon whirling around a white dwarf, a star's corpse compressed to the size of the Earth, spinning fast because, before its companion became a pulsar, it fed on the companion's outflowing matter and swallowed its momentum. Around that fast-spinning corpse, space-time is stirred hard enough that the pulsar's whole orbit slowly tips over, precessing in exactly the manner Lenz and Thirring wrote down. Frame dragging is not an Earth curiosity. It is how the universe works around every spinning mass, everywhere. The next generation of this measurement will not even need a rocket. Far beneath the Gran Sasso Massif in Italy, in the same underground halls that shelter dark matter detectors from cosmic rays, a project called Ginger is assembling ring laser gyroscopes, closed loops in which 2 laser beams race around the same square path in opposite directions. If the loop rotates, one beam's path is effectively stretched and the other's shortened, and the 2 lasers drift out of tune by a frequency difference that measures the rotation absolutely, with no external reference at all. The Sagnac effect, rotation read from the inside, the accelerometer's principle, raised to exquisite sensitivity. A large ring laser in Bavaria, the Gross ring, already senses the Earth's rotation so finely that it can watch the planet's spin axis wobble by centimeters from a basement. Ginger's goal is bolder: to measure, from the ground, the frame dragging of the Earth itself, to detect the rotation of space-time on a laboratory bench. No satellite, no star, no telescope, to about 1%. If it succeeds, The answer to Newton's bucket question will be read out, continuously, by laser light in a tunnel. Here is precisely how much the meaning of not rotating is being stirred, today, by the planet turning over our heads. At the extreme, the dragging becomes tyranny. Around a rapidly rotating black hole, there is a region called the ergosphere, outside the event horizon, where the stirring of space-time outruns light itself. Inside that region, standing still, holding your position fixed against the distant stars, is not merely difficult, it is impossible, in the strict sense that not even light can hold station there. Every particle, every signal, every conceivable thing must co-rotate with the whole, because the local standard of rest itself has been swept into revolution. Think about what that means for our question. Newton's absolute space could never do this. His stage was rigid by decree, the same everywhere, deaf to matter. But near a spinning black hole, matter has seized the stage completely. The thing that defines not rotating is itself dragged into rotation by a nearby body. In the ergosphere, Mach wins, locally and absolutely. And in the museum lobby, watching the Foucault pendulum, you can now hear the full strange chord. The pendulum keeps faith with the distant universe, but not perfect faith, because the earth beneath it spins. General relativity says the spinning planet drags the pendulum's frame of reference around, ever so slightly, a theft of allegiance amounting to those few tens of thousandths of an arcsecond per year. The nearby world does have a say, a confirmed, measured, real say in what counts as rest. That is the down payment on Mach's principle, paid in full and receipted by gravity probe B. Matter demonstrably shapes inertia's compass, but a down payment is not the debt. Dragging the frame a few hundredths of an arcsecond is one thing. Generating the frame, being the whole reason inertia exists at all, as Mach demanded and Einstein hoped, is another entirely. And when physicists pushed general relativity to answer the full question, the theory did something almost cruel. It said no, and it said no to its own creator. That refusal is the strangest turn in this whole story, and it runs through a universe that spins relative to nothing, discovered by a logician who took walks with Einstein at Princeton and quietly handed him a world his theory permitted and his principle could not survive. Every afternoon in the 1940s, two men could be seen walking together across the grounds of the Institute for Advanced Study in Princeton. One instantly recognizable to the entire world, white hair blowing, cardigan sagging. The other, slight, owlish, immaculate, almost pathologically precise. Einstein said in his later years that he went to his office chiefly for the privilege of walking home with Kurt Gödel. Gödel was the greatest logician since Aristotle, the man who had proven that mathematics itself contains true statements it can never prove. And in 1949, as a birthday present for his walking companion's 70th year, Gödel gave Einstein a gift only he could have made, a new, exact solution to the equations of general relativity. It was a universe, and it was a knife. Gödel's universe rotates. Solve Einstein's field equations for a cosmos filled evenly with matter, plus a particular cosmological constant, and Gödel showed you can obtain a world in which the matter everywhere rotates, but rotates relative to nothing. There is no center to the rotation, no axis you can point to, no outside stars to measure against. Every observer in Gödel's universe sees the same thing, and yet gyroscopes and pendulums there would swing and drift in the unmistakable signature of rotation. The whole material content of that cosmos turns with respect to the local inertial frames, with respect, one might say, to the ghost of Newton's absolute space. Now hold Gödel's world up against Mach. Mach's principle says the matter of the universe defines the standard of non-rotation. The fixed stars, in their totality, are the thing the bucket's water answers to. In Gödel's universe, that is flatly false. The totality of the stars there rotates relative to the standard. The matter and the frame disagree, globally, forever. If Mach were woven into general relativity, such a solution could not exist. It exists. Gödel, with the quiet ruthlessness of pure logic, had shown that Einstein's equations permit worlds Mach forbids. And a principle that your own theory's solutions can violate is not a foundation of that theory. It is, at best, a preference. Gödel's universe carried one more property, so notorious that it has overshadowed the rotation ever since. It permits time travel. In that rotating cosmos, there exist closed paths through space-time, routes a patient traveler could follow, always moving forward in their own local time, that nonetheless loop around and return to their own past. Einstein saw this immediately and was disturbed by it, remarking in his published reply that such solutions made him question whether the theory should not exclude them on physical grounds. But he could find no error, because there was none. The universe Gödel built is almost certainly not our universe. The real cosmos shows no detectable global rotation, to remarkably tight limits. But that was never the point, and Einstein knew it. The point was about the theory. What general relativity permits reveals what general relativity is, and it permits worlds where the matter of the cosmos and the standard of inertia simply part company. The knife had a second edge, older and just as sharp. Mach's principle says, no matter, no inertia. A particle alone, in an empty universe, should have no resistance to acceleration, because acceleration would mean nothing. But the very first exact solutions of general relativity had already whispered otherwise. The equations are perfectly happy to describe a completely empty universe. The flat, matterless space-time of special relativity is itself a solution, and in that void, the mathematics still draws geodesics, still distinguishes coasting from accelerating, still hands every test particle a full set of inertial instructions. Willem de Sitter found an expanding, empty universe within months of the theory's birth, provoking Einstein into years of resistance. Solutions describing lone rotating bodies in otherwise empty space carry frame dragging and centrifugal effects with no distant stars to underwrite them. In Einstein's own theory, the stage survives without the actors. Space-time, it turns out, is not the modest bookkeeping of relations between bodies that Mach dreamed of. It is a thing, dynamical, curvable, responsive to matter, yes, but with a life and structure of its own, able to define inertia in a cosmos containing nothing at all. Where does that structure come from, if not from matter? In practice, physicists supply it by hand. To solve the equations, you must specify boundary conditions, assumptions about space-time far away, at infinity, and those assumptions, not the galaxies, end up anchoring the local standard of rest. Newton's absolute space had not been executed after all. It had been demoted, renamed, and rehired as a boundary condition. Einstein resisted, and his resistance shaped his cosmology. His famous introduction of the cosmological constant in 1917, the move he supposedly called his greatest blunder, was made partly in Mach's defense. He wanted a closed, finite universe, curled up on itself with no edge and no infinity. Precisely so, there would be no place for un-Machian boundary conditions to hide. If the cosmos has no far away, then matter is all there is, and inertia must come from it. For years he insisted the theory be read this way, but the solutions kept coming. De Sitter's empty world, the expanding universes of Friedmann and Lemaitre that fit the astronomer's data without any Machian closure, and finally Gödel's rotating impossibility, and Einstein, who prized honesty above even his deepest hopes, gradually let go. His public statements trace the retreat across 3 decades. In his later writings and correspondence, the concession became explicit. One should no longer speak of Mach's principle at all, he wrote to a colleague in 1954, the year before his death. The principle he had named, championed, and built monuments to, He outlived his faith in it. Understand exactly what was lost and what was kept, because the ledger is subtle, and it is the heart of tonight. What was kept? Matter really does shape inertia's compass. Frame dragging is true. Gravity probe B measured it. The pulsar confirmed it. Near spinning black holes, it becomes total. Locally, Mach's intuition scored a permanent, verified victory that Newton's rigid stage could never have delivered. What was lost? The full claim that matter is the whole story, that the distant galaxies generate inertia outright, that without them, your coffee would slosh without resistance. General relativity will not say that. In Einstein's theory, inertia comes from the structure of space-time. Matter bends and stirs that structure, sometimes dramatically, but the structure itself, the thing that holds geodesics open in an empty universe, is an input, not an output. Asked, why does matter resist acceleration? The deepest theory of space and time ever constructed answers. Because space-time has the geometry it has. Asked, and why does it have that geometry, and what anchors it when no matter is present? The theory falls silent and points at the boundary conditions, which is to say, at an assumption. The referee is still employed. He has a new uniform, a new title, and tenure. Mach's principle did not die with Einstein's faith in it. It retreated into mathematics and kept fighting. In 1961, Karl Brands and Robert Dicke, the same Dicke whose torsion balances tightened the two mass equivalents, built a full alternative theory of gravity designed to be more Machian than Einstein's. In it, the strength of gravity itself, Newton's constant, is not a constant at all, but a field, set at each place and time by the distribution of matter in the universe. The far galaxies, in Brands-Dicke theory, literally tune the local laws. For decades, it stood as general relativity's most serious rival, and it was testable. The theory contains a dial, and every increase in observational precision turns the dial closer to pure Einstein. The decisive turn came in 2003, when the Cassini spacecraft, coasting towards Saturn, exchanged radio signals with Earth as those signals grazed the Sun, and the delay, imposed by solar gravity, matched Einstein's prediction to a few parts in 100,000. The Machian dial is now pinned so close to zero that Brands-Dicke theory survives only as a shadow of general relativity. Even the best engineered Machian gravity, confronted with the data, converges on the theory that refuses to be Machian. Nature keeps voting for the unanchored geometry. So gather the whole journey in one place, because we have come a long way from the high chair, and the pieces now form a shape worth seeing all at once before we go on. A child pushes a cup, and the cup pushes back. That resistance is inertia, and Newton wrote its rules without explaining it. The bucket showed the resistance has a referee. Something, somewhere, decides what counts as true rotation, true acceleration. Newton said the referee was absolute space, invisible and eternal. Mach said there is no such thing. The referee is the assembled matter of the universe, the fixed stars governing your pendulum and your bones. Einstein built the arena both of them lacked. Space-time, curved by matter, whose straightest paths are what we call falling, and whose refusal we feel as weight. The referee became geometry. And then Einstein's own equations, in the hands of his walking companion, delivered the verdict nobody wanted. Geometry takes advice from matter, but does not take orders. It can exist without matter, disagree with matter, outvote matter. The referee is real, the referee is physical, the referee is measurably influenced by every spinning planet, and the referee still answers, ultimately, to no one we can name. That is where the classical story ends, with the question upgraded, refined, half-paid, and open. If the answer to inertia is not in the stage and not in the stars, there is one place left to look, and the 20th century looked there with everything it had. Not out at the galaxies, into matter itself, into the atom, into the vacuum, into the machinery that gives a particle its mass in the first place. And there, in the summer of 2012, in an auditorium in Geneva, the world was told the search was over. What was actually found that morning, and what was not, is next. On the morning of the 4th of July 2012, the main auditorium at CERN, the European Particle Physics Laboratory outside Geneva, was full before dawn. Students had camped overnight in the corridor, sleeping bags against the doors, as if a rock band and not a seminar were coming. Seats were saved for the elderly men whose names were on the theory being tested, when the Atlas and CMS collaborations, 3,000 physicists apiece, working deliberately in mutual isolation so that neither could bias the other, put up their plots. The room saw two independent bumps rising from the data at the same place. A new particle, with a mass near 125 giga-electron volts, at a statistical certainty of 5 sigma from each experiment separately, the gold standard of discovery, odds of about 1 in 3.5 million, that chance alone made the bump. The Director General said the words, "I think we have it," and the auditorium rose. In the audience, an 83-year-old Scotsman removed his glasses and wiped his eyes. Peter Higgs had written his paper predicting this particle in 1964, 48 years earlier. The journal Physics Letters had initially passed on the fuller version, and a colleague had once told him the work had no obvious relevance to physics. "It's really an incredible thing," he said that day, "that it's happened in my lifetime." He reportedly celebrated on the flight home with a bottle of London Pride. The next year, Stockholm called. The story of the 1964 papers deserves its minute, because the false dawn had a long, human fuse. 3 groups arrived at the mechanism within months of each other, independently: Robert Brout and François Englert in Brussels, Peter Higgs in Edinburgh, Gerald Guralnick, Carl Hagen, and Tom Kibble in London. Higgs's first short paper was rejected by the journal at CERN, the very laboratory that would find his particle, as not warranting rapid publication. He added a paragraph noting the theory implied a new detectable particle, sent it to an American journal instead, and that added paragraph is why the boson bears his name alone, a fact that embarrassed him lifelong. He was a shy man who disliked the fame, deflected the God particle label with visible discomfort, and always listed the other 5 names. Brout died in 2011, 1 year before the discovery that would have brought him to Stockholm. The Nobel Committee, which does not honor the dead, gave the 2013 prize to Englert and Higgs. Half a century is a long time to wait for the universe to answer a letter. Most of the men who wrote it were old, and one was gone when the answer came. The newspapers, needing a headline the species could feel, reached for the phrase that had followed the particle for decades: the thing that gives everything mass, the origin of weight. Some, borrowing an old publisher's coinage that physicists mostly hated, called it the God particle. And it would be hard to invent a better setup for tonight's question. Because if the Higgs gives matter its mass, and mass is the measure of inertia, then surely, that July morning, the mystery of inertia was solved in a tunnel under the French-Swiss border. This is the moment to do what the headlines could not: the honest arithmetic. It is worth every minute, because what the Higgs actually does is stranger and more beautiful than the slogan, and what it does not do is the reason this video exists. Here is what it does. The Higgs field is a field, like the electric and magnetic fields, a condition of space itself, with a value at every point. But it has one property no other known field shares: empty space is not empty of it. Cool the universe to nothing, remove every particle, every photon, every disturbance, and the Higgs field remains switched on, everywhere, at a constant strength of about 246 giga-electron volts, a number fixed since the first trillionth of a second after the beginning. Space itself, in other words, has a permanent, uniform texture. and certain particles feel it. An electron moving through the vacuum is not moving through nothing. It is moving through the switched-on Higgs field, interacting with it continuously, and that interaction is what physicists mean when they say the Higgs gives the electron its mass. A particle that ignores the field, like the photon, moves at the speed of light and is massless. Particles that couple to it, electrons, quarks, the heavy carriers of the weak force, acquire rest mass in proportion to how strongly they couple. Why the couplings differ, spanning many orders of magnitude from the featherweight electron to the top quark, nobody knows. The numbers are measured, not derived. But the mechanism itself is confirmed. The particle found in 2012 is a ripple in that ever-present field, proof the ocean exists, obtained by making it splash. A useful picture, imperfect like all of them, is a celebrity crossing a crowded room. The crowd is the Higgs field, and the celebrity cannot cross quickly because the crowd clusters around her. She acquires an effective heaviness from the interaction. An unknown guest crosses the same room unimpeded, like the photon. The picture fails in one instructive way. Real crowds resist motion itself, but the Higgs field resists nothing about steady motion. Only the ledger entry, the rest mass, is written by the interaction. Now the audit. Your body is made of atoms. Atoms are electrons around nuclei. Nuclei are protons and neutrons. Protons and neutrons are each 3 quarks. The electron's mass is pure Higgs, and electrons contribute about 1/4000th of an atom's mass. Almost everything you weigh is nucleus, so the question becomes, how much of a proton is Higgs? A proton weighs 938 mega-electron volts in the physicist's units. The rest masses of its 3 quarks, the only Higgs contribution, add up to roughly 9. That is 1%. The other 99% of the proton's mass, of your mass, is not stuff at all. It is confined energy, the furious kinetic energy of quarks caged in a space 100,000th the size of the atom, and the field energy of the gluons binding them, churning at a scale where our vocabulary for motion gives out. That energy has mass, because energy is mass. Einstein's E equals mc squared, run in reverse. M equals E divided by c squared. Trap energy in a box, and the box weighs more. The proton is such a box, and you are made of such boxes. This is not speculation. Physicists can now calculate the proton's mass from first principles, feeding nothing but the laws of the strong force into supercomputers, running the equations on a space-time lattice, and the answer comes out correct to about 1%. When you stand on a scale tomorrow morning, understand what the number reports. About 1% particle mass from the Higgs field, and 99% the weight of trapped invisible fire. Even the units of the modern world quietly agree that mass is deeper bookkeeping than amount of stuff. In 2019, the kilogram itself was redefined. The platinum-iridium cylinder that had reigned in a Paris vault since 1889 was retired because it was, humiliatingly, losing atoms. The world's standard of mass was changing mass. Its replacement is not an object at all. The kilogram is now defined through Planck's constant, realized by an instrument called a Kibble balance that weighs matter against precisely metered electromagnetic force. The standard of inertia on Earth is now anchored to quantum mechanics, to the physics of the very vacuum whose role in inertia remains unresolved. So the slogan was wrong by a factor of 100, but let it be wrong generously. 1% of every atom, and the entire existence of chemistry, is no small gift. Remove the Higgs field, and the electron goes massless. Massless electrons cannot be bound into atoms. No atoms, no molecules, no you. The Higgs is necessary for the world as we know it. And here is the turn. The reason this glorious, Nobel-crowned, half-century-in-the-making discovery leaves tonight's question standing exactly where Newton left it. Look at what the Higgs mechanism actually explains. It explains how much rest mass certain particles have. It is, in the deepest sense, an inventory, the universe's ledger of M's, with a mechanism for how each entry got written. What it does not explain, what it does not even address, is why anything with an M on the ledger resists acceleration. The Higgs field is perfectly uniform and perfectly still. Moving through it at constant velocity costs nothing, produces no drag, no headwind, no resistance. It must be so, because Galileo's ship still sails. Uniform motion remains undetectable, and a field that resisted velocity would betray it instantly. The field only matters when you accelerate, and the fact that acceleration, uniquely, is what matter fights. The fact that the ledger's entries express themselves as refusal, as pushback, as the lurch in the braking bus. That fact walks into the story from outside the Higgs mechanism entirely. F equals ma is assumed by the theory, not delivered by it. The Higgs tells you what m is for an electron. It has nothing whatsoever to say about why m multiplies a. There is a way to say this that makes the gap almost physically visible. The Higgs mechanism and the strong forces trapped fire together answer the question, where does mass come from? They do not touch the question, what does mass do and why? A warehouse inventory, however complete, does not explain gravity acting on the crates or the effort of shoving them. After July of 2012, physics knows, magnificently, precisely, to 5 sigma, where the crates came from. The shove still pushes back for no stated reason. The particle physicists, it must be said, never claimed otherwise. The confusion lived in the headlines, not the papers. Ask the theorists what enforces the resistance itself, and they will point you back out of the tunnel, to space-time, to geometry, to the unfinished business of Newton's bucket and Mach's stars, and Einstein's boundary conditions. The deepest inventory in scientific history, and the oldest question in mechanics, passed each other that morning in Geneva like ships. And yet the Higgs episode changed the mood of the question in one crucial way. It proved, with a particle you can produce on demand, that empty space is not nothing, that the vacuum has structure, texture, permanent fields switched on since the universe began, capable of writing properties into every particle that swims through them. If the vacuum can hand a particle its mass, physicists could not help asking the next question. Could the vacuum also be what pushes back? Could inertia itself, not the inventory but the refusal, be something space does to matter when matter accelerates? At the end of the 20th century, a handful of physicists proposed exactly that, and their idea, along with a stranger discovery about acceleration and heat, opens the final door of the night, the possibility that the resistance in your hands is the temperature of the vacuum, felt from inside. Everything in this part of the night is speculation, and I will keep saying so, because that honesty is the price of admission to some of the strangest ideas in modern physics. Nothing ahead is established the way the bucket, the two masses, and the frame dragging are established. These are the live attempts, the ideas currently on the table for what inertia might actually be, and the reason to hear them is not that any one of them is likely true. It is that each one shows you a different place the answer could be hiding. The first attempt is Mach's, grown up and given equations. In 1953, a young Cambridge physicist named Dennis Sciama, who would become one of the great teachers of the age, doctoral advisor to Stephen Hawking, Martin Rees, and a startling fraction of modern cosmology, published a paper with the boldest title in this whole story, On the Origin of Inertia. Sciama built a deliberately simplified theory, modeled on the mathematics of electromagnetism, in which every mass in the universe reaches out to every accelerating mass with a kind of gravitational induction. Just as a changing magnetic field induces an electric push, in Sciama's model, the relative acceleration between a body and the rest of the cosmic matter induces a drag, and that drag is inertia. The scheme makes the resistance you feel when you shove a cart into a real, calculable tug-of-war with the contents of the universe, dominated, exactly as Mach's arithmetic hinted, by the most distant matter. And it produces one genuinely haunting requirement: for the induced drag to have the strength we actually measure, for F to equal ma with the m's we observe. The gravitational potential of the whole universe at your location must be comparable to the speed of light squared. Run the numbers with the observed density and size of the cosmos, and, to order of magnitude, it is. That may be a numerical accident, but in Sayama's framework, it reads like a signature: the strength of your body's stubbornness, set by a census of everything that exists. His model was a sketch, not a finished theory. He said so himself, and its full incorporation into general relativity never succeeded, for all the Gödelian reasons of the last part. But it remains the most serious attempt ever made to make Mach compute. The second attempt was born in 1994, in the pages of a mainstream physics journal, from Bernard Heisch, Alfonso Rueda, and Harold Puthoff. Their starting point was the quantum vacuum. Empty space, at its floor, is not empty. It seethes with irreducible fluctuations of the electromagnetic field, the so-called zero-point field, whose reality shows up in measurable effects like the Casimir force between close metal plates. Heisch, Rueda, and Puthoff asked, what does this omnipresent fizz look like to a charged particle moving through it? At constant velocity, nothing. The zero-point field has the remarkable mathematical property of looking identical to all uniformly moving observers, so Galileo's ship survives again. But to an accelerating particle, they argued, the vacuum's symmetry breaks. The fizz acquires a directional bias, a radiation pressure headwind, proportional, and this was the electrifying part, to the acceleration. Force proportional to acceleration is F equals ma. Inertia, on this proposal, is literally vacuum drag. Matter resists acceleration, because accelerating through the quantum vacuum is like accelerating into a wind that stiffens exactly in proportion to how hard you push. The idea drew serious attention, NASA study money, and years of scrutiny, and, it must be said plainly, it has not survived that scrutiny well. Critics showed the derivations lean on contested steps. The framework has produced no confirmed prediction that distinguishes it from standard physics, and the mainstream position is that the vacuum's contributions to mass are already fully counted inside quantum field theory's existing bookkeeping. It survives at the margins, unfalsified in parts, unproven in whole, a beautiful mechanism in search of a decisive test. The Casimir force deserves its own breath here, because it is the reason the zero-point field cannot simply be dismissed as accounting fiction. Take two flat, uncharged metal plates and bring them very close together in vacuum. Separations under a micrometer, 1/100th the width of a hair. The vacuum's fluctuations come in all wavelengths, but between the plates, only wavelengths that fit can exist, while outside, all wavelengths press in. The imbalance produces a real, measured force pushing the plates together, predicted by Hendrik Casimir in 1948, measured with precision by Steve Lamoureux in 1997, and routinely accounted for today by engineers designing micro-machines, whose tiny moving parts can be seized by the vacuum's grip. Empty space, in other words, verifiably pushes on matter under the right conditions. The zero-point inertia proposal was never absurd in kind, only perhaps in degree. But the vacuum was not done with acceleration, because the third thread is not speculation at all. It is one of the most secure and most disturbing results of theoretical physics. In 1976, William Unruh of the University of British Columbia proved something that still sounds like poetry, pretending to be a theorem. Acceleration changes what empty space is. An observer, coasting through a perfect vacuum, measures nothing. No particles, no temperature, The void. An observer, accelerating through the identical vacuum, measures a warm bath of particles. Real warmth, a real temperature, proportional to the acceleration. Come ride it for a moment. You are strapped into an impossible rocket, accelerating harder and harder through interstellar emptiness. Behind you, an event horizon forms, a surface beyond which light can no longer catch you, your own private edge of the universe, receding but never releasing. And ahead, the vacuum itself begins, very faintly, to glow. The nothing acquires a temperature. At 1 Earth gravity of acceleration, the unruh temperature is about 4 times 10 to the minus 21 Kelvin, 20 orders of magnitude colder than the space between galaxies, hopeless to detect directly, which is why no one has. Laboratories are even trying to hear these horizon-born whispers by analog. In Haifa, Jeff Steinhauer's group builds black holes out of sound, a Bose-Einstein condensate, a cloud of atoms colder than anything in nature, made to flow faster than its own speed of sound, so that sound waves trying to escape upstream are trapped exactly as light is trapped by gravity. In 2016, and with a measured temperature in 2019, the group reported the acoustic analog of Hawking radiation rising from that sonic horizon. Proposals exist to chase Unruh's glow directly with petawatt lasers, whose electrons can be accelerated at some 10 to the 25 G, hard enough, briefly, to warm the vacuum toward visibility. But the effect is not fringe. It drops out of quantum field theory the way Hawking radiation drops out of black holes, and it is the same mathematics. Horizons make heat. Acceleration, the one thing matter resists, is precisely the thing that gives the vacuum a temperature. It is very hard to look at that sentence and believe it is a coincidence. Some physicists have refused to believe it is. In 1995, Ted Jacobson produced a derivation that startled the field. Assume only that heat, entropy, and temperature behave thermodynamically on the tiny horizons seen by accelerating observers, and Einstein's field equations, all of general relativity, fall out as a consequence, the way the gas laws fall out of molecular statistics. Gravity, on this reading, may be an equation of state, not a fundamental force, but a statistical summary of something deeper, as temperature is a summary of molecular motion. Eric Verlinde pushed further in 2010, arguing gravity and inertia are both entropic, that matter resists acceleration for the same statistical reason ink spreads in water, because of how microscopic information rearranges. And at the far contested edge stands Mike McCulloch's quantized inertia, which proposes that Unruh radiation, filtered by horizons, literally is inertia, and claims, as its selling point, to predict from first principles the one number in the sky that keeps this whole family alive. That number deserves its own moment, because it is real, it is measured, and nobody can explain it. Galaxies rotate wrong. Below one particular acceleration, about 1.2 times 10 to the minus 10 meters per second squared, stars orbit as if Newton's laws lose their grip, the observation usually credited to dark matter. Mordechai Milgrom noticed in 1983 that you can instead fit the data by modifying inertia itself at tiny accelerations, and the threshold acceleration is, within a small factor, the speed of light divided by the age of the universe. Read that again. The scale at which inertia seems to falter matches the size and age of the cosmos, a whisper of Mach, written in telescope data, unexplained by the standard picture, and unexplained, honestly, by anyone. The current battlefield is wide binary stars, pairs orbiting each other gently enough to probe that regime. Since 2023, rival analyses of the same satellite data have reported opposite verdicts, some finding pure Newton, some finding the anomaly, and the dispute is live as we speak. There was even a spacecraft-sized scare along the way. Through the 1990s, tracking of the Pioneer 10 and 11 probes, coasting out beyond Saturn, showed both decelerating by an unexplained hair, about 8.7 times 10 to the minus 10 meters per second squared, suspiciously near the galactic threshold. For a decade, it was the most famous anomaly in physics, cited by every modified inertia paper written. Then, in 2012, a painstaking thermal reconstruction of the aging probes showed the answer: heat. The probe's plutonium power sources radiated more warmth from one side than the other, and photons leaving preferentially forward braked the craft by exactly the missing amount. The anomaly died, and its death is the sober lesson this family must carry. At these tiny accelerations, almost everything looks like new physics until someone counts the heat. Hold the whole family in view and notice what its members share. Saima's cosmic induction, the zero-point headwind, Unru's warm horizons, entropic gravity, quantized inertia. Every one of them, whatever its fate, is a bet that inertia is not fundamental, a bet that F equals ma is a summary, an average, a macroscopic law like the laws of heat. True the way hot air rises is true, while beneath it, something else entirely does the bookkeeping. If any version of that bet wins, then the resistance in your hands is not bedrock, it is weather, the large-scale forecast of a microscopic sky no one has seen. And perhaps the strangest thing you will hear tonight is that physics cannot currently rule that out. Wherever physics admits it does not understand something, a dream moves into the vacancy. For inertia, the dream has always been the same one, the off switch. If nobody knows what makes matter resist acceleration, then nobody can prove the resistance is non-negotiable, and a civilization that could negotiate with inertia could cross the galaxy on a teacup of fuel, corner at right angles, and shrug away every crash. Science fiction installed the dream decades ago under the name inertial dampers, and every few years, someone announces they have found the switch. What follows is the honest history of those announcements, told not to mock them, but because how physics answers them is one of the most instructive spectacles in science. The cultural soil was prepared long before the laboratories got involved. Generations raised on starships that bank like fighter planes have already internalized the premise that inertia is an engineering problem. The fictional dampers exist precisely because writers noticed that their ship's maneuvers would turn crews to paste and patch the physics with a word. The patch worked so well that the word now does the believing for us. It is genuinely difficult, after a lifetime of such stories, to feel how radical the claim of an inertia switch actually is. It is a claim against every collision, every orbit, and every conservation law ever measured. The largest of them began around 2001, when a British engineer named Roger Scheuer began promoting a device he called the M-Drive, a sealed, truncated copper cone, fed with microwaves, with no exhaust, no propellant, and no moving parts, which, he claimed, produced thrust. A closed box that pushes itself is not a small claim. It violates the conservation of momentum, the law joined at the hip to Newton's laws, the principle that in 3 centuries of measurement has never blinked, the very law we watched hold from the high chair to the pulsars. Physicists' reaction was accordingly blunt, but the claim refused to die, because every so often a laboratory would test a copy and report a whisper of thrust. The whispers were micronewtons, the weight of a grain of sand, but they kept coming, from more than one country. In 2016, the story detonated. A small NASA team at the Johnson Space Center, known as EagleWorks, published a peer-reviewed paper reporting measured thrust from an M-drive in vacuum, around 1.2 millinewtons per kilowatt. The internet did what the internet does. The impossible drive. NASA confirms physics is broken. For a season, the off switch seemed, to millions of people, to have been found in Houston. What actually happened next is the part worth remembering forever. A German team at the Technical University of Dresden, led by Martin Tajmar, a physicist who specializes in testing exotic propulsion claims seriously rather than dismissing them, spent years building the most careful M-drive test rigs ever assembled, with thrust balances able to resolve forces far below the claims, inside shielding designed to strangle every source of false signal. And one by one, they found the whisper's true voices, power cables carrying current near the Earth's magnetic field flex, microscopically, like compass needles, producing exactly the kind of tiny apparent thrust the earlier rigs had seen. Heated components expand, shifting the device's center of gravity on its balance. Another false thrust, this one even reversing direction as things cool. By 2021, Tajmar's group had reproduced each reported signature and shown each one vanishing once the mundane cause was controlled. Fed with full power, measured properly, the M-drive produces nothing, zero. Momentum conservation had been prosecuted with every resource, and it walked out of the courtroom without a scratch. Notice what actually defended the law. Not authority, not ridicule, better instruments. The claim was extraordinary, and science answered it in the only currency that counts. The M-drive had ancestors. In 1992, a Russian materials scientist named Eugene Podkletnov reported that objects suspended above a spinning, superconducting ceramic disc lost a fraction of their weight, up to about 2%, he said. Gravity shielding, a material that partially blocks the pull, which would demolish the equivalence principle we spent an earlier part of tonight polishing to 15 decimal places. The claim was published, retracted from a follow-up journal amid controversy, and never replicated, but it was taken seriously enough that NASA's Marshall Space Flight Center spent years and considerable money attempting to reproduce it with a purpose-built superconducting rig. They found nothing. No shielding, no weight loss, no effect. The dream retreated again, and resurfaced, as it always does. In 2016, a US Navy engineer named Salvatore Pais filed a patent application for an inertial mass reduction device, alongside sibling patents for a room temperature superconductor and a compact fusion reactor. The patents were granted, a fact breathlessly cited across the internet as proof the military possesses secret inertia technology, especially once the filings surfaced during a period of intense congressional interest in unexplained aerial phenomena. The unglamorous truth: patent offices do not require working devices. The Navy itself eventually confirmed that experiments based on the Pais concepts found no supporting evidence, and no data from any of it has ever been produced. A patent is a fence around an idea, not a demonstration that the idea breathes. Two details of the M-drive years complete the picture. Scheuer's own theoretical justification invoked special relativity, which is a self-inflicted wound, because special relativity is precisely the framework in which a closed box cannot push on itself. The theory he cited as his engine is the theory that forbids his engine. And for a while, the story acquired a geopolitical subplot. Around 2017, Chinese state media reported that researchers had tested an M-drive and were preparing space trials, which fed a minor arms race anxiety in the online discourse. No verified demonstration from any country ever followed. Extraordinary machines that work get replicated, scaled, and shipped. Extraordinary machines that do not work get press releases. The same era hosted a subtler, more respectable cousin. James Woodward, a historian of science and physicist in California, spent decades pursuing what he called Mach effect thrusters, devices built on Sayama-style inertial induction, proposing that a capacitor, whose energy changes while it accelerates, should fluctuate minutely in mass, and that pushing on it in rhythm with those fluctuations could yield net thrust without propellant, momentum being exchanged, in Woodward's telling, with the distant matter of the universe itself. Unlike the M-drive, this idea at least has a pedigree reaching back to real physics. It is Mach's principle, weaponized for propulsion, and it earned funding from NASA's Innovative Advanced Concepts program, which exists precisely to give longshots a fair hearing. The fair hearing arrived in the same Dresden laboratory that killed the M-Drive. Tajma's group built and tested Mach effect thrusters with the same obsessive controls, and reported that the observed thrusts were vibration artifacts, the device shaking itself against its balance, vanishing when properly isolated. DARPA, for its part, funded Mike McCulloch's quantized inertia program from 2018 to 2022, with a similar long-shot rationale. The associated laboratory thrust claims have likewise failed independent replication. The pattern is now almost liturgical. A theory of inertia implies a drive. A bench reports micronewtons. Dresden builds a better balance. The micronewtons die. It is easy to file all this under human folly, but do that and you miss the real lesson, which is double-edged. Edge 1. Inertia has now been stress-tested by its enemies. Every off-switch claim forced the instruments to improve, and every improvement found conservation of momentum and the equivalence principle standing exactly where Newton and Einstein left them. The null results are themselves data, among the strongest we have, that inertia offers no handle, no shield, no loophole at any technology level our species has reached. Edge 2, and say it quietly, the dreamers are not wrong that the door is unlocked. The reason the off switch cannot be ruled out by pure theory is the whole thesis of tonight. Physics does not know what inertia is. A thing without an explanation is a thing without a warranty. If inertia turned out to be vacuum weather, as the last part imagined, then in some unimaginably remote sense it might have conditions, and that faint, probably false, unforeclosable possibility is the flame the moths keep finding. The mainstream and the fringe are, in the end, staring at the same vacancy. One of them furnishes it with patents. The other leaves it empty and calls the emptiness by its correct name, open question. And an open question is a compass. Because if 3.5 centuries of genius have neither explained inertia nor found its edges, if the stage failed, and the stars failed, and the geometry went silent at the boundary, and the inventory came up 1%, then the honest move left is the one this whole night has been building toward. Stop asking who has the answer. Ask instead why the question has defeated everyone, because that, it turns out, has an answer, and it is time to give it. At the beginning of tonight, I made you a promise that we would end by answering the question in this video's title. Not the question of what inertia is. You have watched 4 centuries of genius fail to settle that, and I will not pretend to succeed where Newton and Einstein did not. The question we can answer is the one the title actually asks. Why? Why can no one explain the simplest concept in physics? Why does the first law a child ever tests remain, after 350 years of triumph after triumph, an axiom with no flaw beneath it? Here is the answer, and now you have everything you need to feel its full weight. Every explanation of inertia that has ever been attempted, every single one, across 4 centuries, turns out to require the universe to hold something fixed. Some anchor, some reference that does not move, so that motion against it can have a meaning, and resistance to that motion can have a cause. Newton held space itself fixed, an absolute stage, and inertia was matter's grip on the stage. The stage explained everything, and could never be found. An anchor made of pure assertion. Mach held the matter of the universe fixed, the fixed stars as the anchor, the whole freight of creation gripping every bucket of water. The grip was real enough to feel, but no mechanism was ever written down that survived. Einstein held the geometry fixed, not rigidly. His space-time bends and flows, and can be stirred by a spinning planet, and that stirring has been measured by the most perfect spheres our species has ever made. But at the bottom of his equations, out at the boundary where the mathematics needs its footing, the anchor reappears, assumptions about space-time at infinity, chosen by hand, doing quietly the exact job Newton's stage did loudly. And the moderns hold the vacuum fixed, a Higgs field switched on identically everywhere, writing the inventory of mass, a zero-point C whose horizon-warmed weather might be the resistance itself. Every road, without exception, ends at an anchor, and no theory in existence explains its own anchor. That is the answer. No one can explain inertia, because explaining it requires naming the thing the universe holds fixed, the referee behind every push, and every candidate referee has either dissolved under inspection or turned out to be an assumption wearing a uniform. Physics has not found the thing that holds the anchor. It is not certain there is a thing. It is not even certain the question is the kind that has that kind of answer. And so the honest state of knowledge, tonight, is a choice among three universes that all look exactly like yours. In the first, inertia is bedrock. A brute fact, fundamental, uncaused, the way the universe simply is. And the search for a mechanism was always a category error, like asking what the number 3 is made of. In the second, inertia is a relationship. Mach was essentially right. The anchor is everything. And some future theory, quantum gravity perhaps, or cosmology with the right boundary, will finally write the equations that tie the resistance in your wrist to the contents of the whole sky, finishing the letter Syama, started in 1953. In the third, inertia is weather, an emergent statistical thing, an average over some deeper vacuum bookkeeping, true the way temperature is true, in which case F equals ma is not a law but a summary, and somewhere out at the faintest accelerations, where the galaxies already misbehave around 1.2 times 10 to the minus 10 meters per second squared, the summary is quietly coming apart. Bedrock, relationship, or weather. Every experiment ever performed is consistent with all three. Somewhere in the falling atoms of the interferometers, in the underground rings waiting to feel the planet stir space-time, in the disputed orbits of wide binary stars, the vote is being taken now. It is worth one quiet minute to imagine the morning after, the day one of those three universes is confirmed, because the stakes are not academic. If bedrock wins, physics finally learns where its flaw is. The discipline gains, for the first time, a proven boundary between what can be explained and what must be accepted, and that alone would change how every deeper theory is judged. If relationship wins, then cosmology and mechanics fuse. The mass of an electron becomes a statement about the census of galaxies. The laboratory and the sky become one instrument, and constants we treat as local property turn out to be rented from the universe at large, with all the strange, remote implications that renting implies. And if weather wins, if inertia is emergent, statistical, a summary, then somewhere beneath F equals ma, there is machinery, and machinery, unlike bedrock, has parts. No one should promise what understanding the parts would permit. The M-Drive graveyard warns us how that story usually ends. But every law physics has ever understood more deeply, it has eventually learned to work with more cleverly. Heat became engines, fields became radio, the quantum became the device you may be listening on. The one law we lean on hardest is the one we have never once seen the inside of. Whichever way it falls, the answer will have been purchased by the patient machines this night has visited. The torsion balances still turning in Seattle, the atom fountains in their towers, the quartz spheres now silent in orbit, the lasers underground listening for the planet to stir the dark. Notice, before we put the question down, what it has been doing to everyone who pushed on it, because this is the strangest symmetry of the whole story. A child pushes a cup, and something pushes back. Newton pushed on the question, and absolute space pushed back. Unfindable, immovable. Mach pushed, and the stars pushed back, refusing to yield a mechanism. Einstein pushed harder than anyone, got closer than anyone, and near the end of his life, with a lifetime's honesty, admitted that the thing had not moved. The principle he named for his hero could not live inside the theory he built for it. The Higgs hunters pushed for half a century and moved the question 1%. Something pushes back. It always has. The resistance you feel when you push on matter, and the resistance the species feels when it pushes on this question, have the same shape, as if the concept itself possessed the property it describes. The simplest concept in physics defends itself with its own inertia. Perhaps that is the right image to fall asleep inside. Not a failure, a frontier that happens to run through your bedroom. Because think of where the fixed stars have ended up in this story. Mark's phrase was always slightly wrong. The stars are not fixed. They burn and drift and orbit and die. The constellations dissolve over ages like slow smoke. And yet the covenant holds anyway. Tonight, as the planet carries your bed eastward and swings you around a burning star that is itself falling around a galaxy, the pendulum in the darkened museum keeps its plane locked to the frame of matter so distant it has no names. And so does the fluid in your inner ear, and so does every atom of you. Whatever signs that agreement, stage, stars, geometry, or the warm static of the vacuum, it has never once failed to co-sign your existence. Every step you have ever taken was countersigned by something that spans the sky. You do not need physics to settle the question before you trust it with your sleep. You have trusted it with every heartbeat so far, and it has never dropped you. The universe is holding something fixed for you. It simply has not told us what. Thank you for spending this night with the oldest question in mechanics, the one hiding inside the first push you ever gave the world. If an unanswered question, held up to the light this slowly, is your kind of company after dark, a like or a subscribe would mean a great deal to me. It is a small thing for you, and it is what keeps these long nights possible. And remember, the next time you nudge a cup across a table and feel that small, patient refusal, you are touching the simplest concept in physics, the one that no one, anywhere, can yet explain. Good night, and may you never feel the world push back the same way again.